In this section, we're going to look at the creation of mountains. This is a really nice follow-up to oceans because oceans are born at divergent plate boundaries, but the oceans are killed at convergent plate boundaries. Of course, that's how mountains are created though. So let's look at some of these details. Most, but not all mountains are created at convergent tectonic plate boundaries. With the exception of large volcanoes formed over hotspots, these mountains do not occur in isolation, but rather as part of an elongated range called mountain belts or erosions. This map shows a number of the major erosions throughout the world. In particular, ones you're probably familiar with are the North American Cordillera, and that covers a really large portion of the entire western part of the United States. Other ones we've talked about before are the Andes, the Appalachians, and the Himalayas. And we're going to look at how each of these areas formed as we go through this. The mountain building events are known as orogenies that create these mountain belts. These may last for tens of millions of years. Now, there's places that haven't had a lot of mountain growth, and there are places that have had a lot of mountain growth, and so that's what this map here is showing you. So the yellow is fairly young mountain belts, and you can see these are the ones that are all sort of actively growing right now. There's old mountain belts like the Appalachians and the Caledonians. These both formed at the same time when Pangaea was created. The Urals, which formed when Europe and Asia ran into each other. But there's also these areas called shields. And a shield is part of a craton. So crust that hasn't been affected by orogenies for the last billion years at least is known as a craton. These areas are exposed, really old, really deformed metamorphic rocks. So we're talking Precambrian, billions of years old. And those areas that have metamorphic rocks are known as the shield. Cratons also have what's called the cratonic platform, and that's what you see in this map of North America. You can see the Canadian Shield. This is where you can go to see really, really old rocks. But surrounding it is the cratonic platform. And the cratonic platform is part of that really stable old continental material, but it's covered in a thin layer of sedimentary rocks. Now, what's interesting is that mountains are areas that have significantly higher elevations than surrounding areas. But the elevation of the surface depends on the thickness and the density of the crust. But mountains are deep or even deeper into the mantle than they are tall above the surface. The crustal material can move up and down due to this process called isostasy or isostatic equilibrium. And this is the process in which buoyant force pushing up on the lithosphere equals the gravitational force pulling it down. And that's a lot of big words. But basically what happens is the crust sort of floats on the mantle. And so think of this as like a boat in the lake. That's what these wooden blocks represent. If you were to come and stand right here on this middle block, you'd push it down into the water, right? And if you hop back off, the block would pop back up. Well, that's exactly what the crust does. So when you add mountains, you add extra material because of the mountains. The crust pushes deeper and down into the mantle, and if that material is moved, like through erosion, that material rises back up, which is actually kind of interesting. And here you can see that as well. Your high mountains make for the lithosphere going down really deep into the asthenosphere. Now, mountains can't just grow forever, infinitely tall. There's a limit to how tall they can get. There's lots of processes that start eroding them. Landslides carry rock and debris down to the foot of the mountains. Streams and glaciers erode valleys and canyons and also carry that material away. As this material is eroded from the top, the mountains will start to uplift because of that isostatic rebound. So you take material off the top and the whole crust rises up again. And so these two processes are in a really delicate balance between how short they're getting due to erosion, but how tall they continue to get because of uplift. For very tall mountains like the Himalayas, the roots of the mountains go really deep into the mantle. And if you remember, the mantle is really hot. And granite is a felsic rock, which means it has a fairly low melting temperature. So as it gets deeper and deeper into the mantle, as the mountains get taller and taller, that material at the bottom starts getting really soft. And starts to kind of melt. And what happens is you get delamination, which is what's in this picture. And so parts of the very bottom of the crust will actually peel off and move away. And the mountains then collapse down under their own weight because they're no longer supported in the mantle. And that's one of the biggest things right now that contributes to how tall the Himalayas can get. And so here's another example of the effects of isostasy. If we rewind the clock back by about 18,000 years, pretty much all of Canada and a good portion of North America was actually covered by glaciers during the last ice age. So that 15,000 to 18,000 years ago is what we refer to as the last glacial maximum. And all that weight from all of that ice pushes down on the crust. But obviously that material isn't there anymore and all the ice is melted. So what's happening is the crust is actually rebounding and rising back up now that that weight is gone. In the map on the right, you can see Canada. And what this map shows is the isostatic rebound in North America for the past 6,000 years. And so these contours shows you areas that have risen the same amount. So for this line, it's just like a topographic map, right? This line has risen by 70 meters. This one has risen by 80. And there's portions up here that have actually risen by 100 meters. That's what, like 300-ish feet? That's a really big rise in just 6,000 years. Now, interestingly enough, if you look at some of these Great Lakes, there are some Great Lakes that the northern part is rising faster than the southern part. And that actually leads to dry docks in the northern part and flooded docks in the southern part. If you look further down, that area around the Great Lakes is riddled with faults. And even going down through the Mississippi River Valley those areas have really old faults. And as the entire northern part of North America is rising, it's actually reactivating those faults, and it contributes to a lot of earthquakes that happen sort of outside of that west coast active tectonic plate boundary. So what we're going to do now is we're going to look at the 3 ways that mountains are created. The first way is its subduction. So subduction occurs at convergent plate boundaries where oceanic crust is forced down into the mantle. We all know this already. These interaction between the two plates creates compressional stress, and you get deformation structures. And we've talked about those. Remember our faults and folds? So on the continent, you get thrust faults as well as anticlines and synclines. Oh, here you go. Here's you a continent, an ocean continent crust. This is a passive plate margin, but once everything starts pushing, there you get subduction. And so that compression actually folds all of the sediment up that was in along the edge of the continent. And these are what's known as these are thrust belts. You also get anticlines and synclines here. Those are all structures from compression. It creates these areas known as fold and thrust belts because it's made of, well, folds and thrust faults, and that's kind of obvious, right? You get significant shorting horizontally and surface uplift, which is sort of interesting, right? So the area here on the continent gets taller and taller and taller. Now, this is going to happen from a number of reasons. One of the things that happens is as that lithosphere subducts, you get melting in the mantle, in which you get these plutons of melted magma that rise up through the crust and the lithosphere. Some of those actually are able to reach the surface and they create volcanoes. These are known as a continental volcanic arc. Or sometimes they just stall out in the middle and they harden, cool and harden into granite. And so this is one of the ways that the crust gets thicker, is by the addition of this igneous material, both at the surface as volcanoes or in the surface as those big granitic plutons. You can see where all of these materials that were on the continental shelf have started to fold up. And this kind of area here, it all sort of gets all jammed together right at the plate boundary. This is what's known as an accretionary wedge or an accretionary prism. Interestingly enough, sometimes this gets really big, and there are cases where that accretionary wedge actually is large enough and tall enough to peek out above the ocean. So, like the islands of Barbados is actually an accretionary wedge. It just happens to be particularly tall. So the places we're going to find stuff, mountains being created this way, are like the Andes and the Cascades. And the Andes are down the western coast of South America, and the Cascades are down the western coast of North America, or our Pacific Northwest area. Now, what's interesting is, so over time you can see the development of here. The subduction is ended. You have no more volcanoes. Everything is starting to erode. But what you end up with was this mountains that are from the accretionary wedge, a big basin that represents the gap between the wedge and your volcanic arc, and then you have what's left of your volcanic arc. This is exactly what we see in the Pacific Northwest. So this is Oregon. There's Portland and there's Salem, Oregon. You've probably heard of those. So the Olympics down the Pacific Northwest coast, these are actually represent the accretionary wedge. Portland, Salem, even on up in Seattle, those are in what's this area known as the Four Arc Basin. And then you have your Cascades as the volcanic arc behind there. And so the only place we see it, that's an active subduction zone still. But if you go further south, this is exactly what you find in Southern California too. Because interestingly enough, Southern California actually used to be a subduction zone, where the Farallon plate was being subducted under the North American plate. And so the rocks along sort of the western coast of California, these are all from that accretionary wedge. The rocks here are also often known as the Franciscan complex. They're all sorts of messed up just because they've been faulted and folded so much. And then inside the Great Valley, remember the San Joaquin Valley with all of their groundwater problems? This is that Four Arc Basin, and then off to the Sierra Nevada, which is all made of granite and does represent the internal structure of the mountains that or the volcanoes that used to be there. So even though this area hasn't had subduction in like 30 million years, the topography still shows us signs of where that used to happen. One of the other sort of interesting that happens thanks to subduction is a lot of times you'll get extra little pieces of crust floating around the ocean that ends up slapped up on the side of the continent. So in this case, this is an old volcanic island arc. And as that plate is subducting, it's pulling those volcanoes closer and closer and closer, and eventually they get slapped onto the side. This is called accretion. And so these pieces of crust that are added onto the side of the continent may have really different geologic histories. So, for instance, in this case, it was a volcanic island arc that's been added on. And so we tend to refer to these as terranes or sometimes exotic terranes. And this is how continents grow bigger. So if we look at the western part of the United States, most of this is stuff that's been added on fairly recently versus parts of like the continent that have been there a long time. So you can see the craton over here. And that's 1 billion years old, even more so. These are really old, so these have been there. But all this really colorful stuff out here has been added over time. And it doesn't show up well on this map showing you the rocks of Arizona. But the Bradshaw Mountains are a place in Arizona that's really famous for their gold deposits. And one of the reasons why there's so much gold in there is that actually used to be a volcanic arc. So that's one volcanic arc that was added on. There are chunks of the rocks that make up Prescott was another volcanic arc, and chunks of rocks that make up Jerome was even a third one. And so all of those have been added on over time, and they represent some of our really important mineral deposits. Now, so subduction zone we saw makes mountains thanks to crustal thickening from volcanic activity and from igneous activity intruding into the subsurface. Now we're going to look at continental collisions, and this represents our traditional idea of mountains. So when an oceanic plate is completely subducted under, the two continents on either side of that ocean end up colliding. This creates large thrust faults in which the edge of one block slips up and over the margin of the other. Slivers of oceanic crust that are known as ophiolites may be caught between the two plates and be pushed on to the continental crust. There's a really famous ophiolite sequence up in Payson, if you're ever up there looking around. This continental collision creates compressional stress, just like we saw at the subduction zone. And this deforms rocks into reverse faults and folds such as anticlines and synclines. It's the folding and the thrust faults that contribute to the crustal thickening in this case. In addition to the crustal thickening, you also get really high-grade metamorphism. And if you remember when we did metamorphic rocks, we looked at that increasing grade as you go into the interior of mountain belts. And in this picture, this is kind of a silly diagram, but I think it shows really well that crustal thickening. So you started out with one layer of rock, or one sequence of rock layers at least. You had the blue, the green, and the orange rocks. And as all of that was, as you had either edge shoved on top of each other, you had 1, 2, 3 thrust faults. And as those 3 thrust faults stack the rocks on top of each other, now instead of just those 3 layers worth of thickness like we started with, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it's 12 thicknesses of those same layers, which is pretty impressive in terms of thickening there. And so this is why mountains are really tall in these locations. The collisions between continents and small continental blocks or island arcs cause the continent to grow larger as well. And where these blocks run together, we refer to this as a suture. One of the most famous examples of this happening is the collision of India with Southeast Asia. And so you can see this is actually a really quick process. India was pretty far south, only 71 million years ago. So if we rewind back in time, you can see India moving towards Southeast Asia. You have this chunk of continental crust with passive margins on either side. In the middle of the cross section, we have the Tethys Ocean, and that oceanic crust is being subducted under Tibet, or at least where Tibet is now. And over here, you had your traditional subduction zone that we looked at earlier with a volcanic arc, the accretionary wedge, all of that sort of stuff happening. But eventually, that's completely closed up, and those two are sutured together. And that's what's creating the Himalayas as we know them now. That really high-grade metamorphic rock is right in the middle. You can see fragments of that oceanic rock that are buried still. And there are places where you can discover that out there. Now, the Himalayas, or even the Alps, are very young examples of mountains that are formed due to continental collision. But ancient mountains like the Appalachians formed exactly the same way as well. And I know we covered that just a little bit in the oceans. There's one last way to make a mountain, and this one's a little different than the other two. Continental rifting occurs at a divergent plate boundary, and this creates tensional stress. So movement along normal faults creates drop-down blocks of crust that we know as grobens. And they also create small sets of elongate mountain ranges that separate these downdrop blocks, and those are known as horst or fault block mountains. And we've talked about horst and grabes before because the southwest portion of the United States is a beautiful example of these throughout the basin and range region. So this is sort of a before and after shot of what the basin and range looks like. On the left is the before shot with everything all scrunched up together. And then crustal stretching and crustal rifting happened and pulled everything out to as we know it now. So in this case, crust is thinned rather than thickening like we've seen in those other cases. Because the mantle starts to melt thanks to decompression melting, and it forms volcanoes throughout the region as well. So let's look back here. This is the Sierra Nevadas, the Rocky Mountains, and you've got subduction of a tectonic plate under there. And this is creating all that beautiful compression and faults and folds and volcanoes like we talked about before. But at some point, the plate boundary actually changes. That subduction ends. And what happened here is this is the Farallon plate. This is the Pacific plate, and it was spreading. And there's a spreading ridge that ended up being subducted under. What that does is it creates lots of tension that's under the surface. That makes this, it creates the San Andreas Fault along the coastline. And so the type of plate boundary there changes. But it also creates lots of uplift and extension thanks to upwelling between the Sierra Nevada and Rocky Mountains. And if you remember from our oceans, that upwelling is our very first step in making an ocean. And so this is going to create lots of rifting and create the basin and range province that we know now. So that's why we have mountains like South Mountain, like the McDowells, and like the Sierra Estrellas that surround the valley. So the western portion of the United States is actually pretty interesting because we've had periods of both mountain buildings thanks to subduction and mountain building thanks to rifting. So we have both of those here, and I guess you could throw a few of those Continental Collisions that during the accretion of terranes onto the edges of it too. But I wanted to show you a quick little video. There it goes. I don't think the sound is on, so hopefully this works for us. So I'm going to hit play. And when we start here, you're going to be able to see, here's your Farallon plate and the Pacific plate. Here's that divergent plate boundary, that mid-ocean ridge. And here is where the mid-ocean ridge ends up being subducted. And you can see as that ridge is subducted, it causes lots and lots and lots of stretching out west. And that gives you the formation of the San Andreas. That also gives you the basin and range province that we have at this point. So these processes give us mountains, which make incredible landscapes. And as big and as unchanging as mountains seem, they're in a constant battle between erosion and uplift and collapse along the bottom of the lithosphere. So these are actually really dynamic, really changing geologic environments.